Signature Cosmological Physics series with talks on dark matter and dark energy, the primary constituents of the universe. And my own personal opinion is, even if they weren't the primary constituents, they're the most interesting. And there's a lot of action going on there. Let me remind you of the format of these talks. So we're going to have two talks, slightly shorter than the ordinary colloquium. Each one is going to be 45 minutes with no discussion in between, unless there's an absolutely, so no discussion if there's a clarifying question, maybe like that. And then we reserve 30 minutes afterwards for really lively, moderated discussion. So we'll have ample time, and then after that we have a nice reception outside this room. Our two speakers really need no introduction, and not only that, I don't have enough voice to actually introduce them. So one sentence for each of them, and I'll introduce both of them now, and that will save us a little bit of time. So Rocky Cobb is the Arthur Holly Compton Distinguished Service Professor and Dean of the Physical Sciences, and no one has done more to bring the fields of particle physics and cosmology together than Rocky. So that's Rocky's sentence. Wayne Hu is the Horace B. Horton Professor, and no one has done more to turn the phrase precision cosmology from oxymoron to reality. We, while you were, chatting and so on and so forth, we were in the back room and we tossed a coin, and Rocky called heads, and he elected deferred. He deferred. He thinks he's got better defense than offense, I guess. And so Wayne will be the first speaker. So please welcome Wayne Hu.
So I probably should start out by explaining what I've got on this slide. So over break, I was at a general relativity conference celebrating, was in Japan, so they're celebrating 25.
Could you speak louder? Microphone.
Still not? So anyway, it was after the conference, break, and I was walking through the hills in Kyoto. And if you're in Kyoto, there's a beautiful shrine, an artist shrine, where there are these vermilion gates that are covering the landscape of Kyoto, and you walk through these endless series of red torii gates. And so I was thinking about this talk and thinking about the word future in this talk. And I had this dystopian vision of the future, which was this. Me, as I was passing through all the gates turned into giant lambdas, which are the cosmological constant. And worse yet, they were all finely separated. So it appeared like the whole series of hills were discretons of these gates that I was passing through. And each one was like this little bit different, fine-tuned to this enormous amount covering this enormous landscape, which we'll recognize as this analogy for the string landscape, and one of the possibilities that is indistinguishable from cosmological constant, and there's just many, many different vacua, and we happen to be living in our version for the reason that we have to exist, and all of them could be populated in this landscape. That would be a dystopian vision of the future. I'm not here to give you a dystopian vision of the future. The analog from the observational side of the dystopian future is marching forward. You'll see there's great progress on the observations, and that really is exciting. But the dystopian vision on that side would be that if we continue to go through from 2016, 2017, and we continue to pass through these giant gates, which are a test of our lambda cold dark matter cosmology, and we continue to see lambda, dystopian visions of the future were true, then LA and New York and even Chicago would be long destroyed. So dystopian visions actually don't often come true. And what we're in the phase now is, with these precision tests are really testing the fundamentals of how well we understand dark energy, looking for the cracks. And in fact, in this picture itself, you'll notice that, in fact, those gates are not lambdas. They're, in fact, more shaped like pies. So this vision of the future is in 2017, these cracks will open up, these Tory gates will collapse, and what will be behind them is a pi symbol, which at the end of the talk I'll talk about one of the ways of thinking about how to think about the framework of what could be beyond the cosmological constant is to think about anything that is consistent with having a homogeneous isotropic cosmology, which of course is well tested, which means that in terms of thinking about this in this language is that we're looking for anything that's consistent with unbroken spatial diffeomorphisms, which is that the universe is translationally invariant, with a broken time direction where the dark energy could be something more than a cosmological constant, could be something dynamical. And in this vision of the future, it opens up with these new experiments like DES, and these cracks really collapse the pillars of these gates into a vision of the future which is not dystopian. So let me recap a little bit about the evidence for accelerated expansion that was discovered and still how it's best tested, which is through measuring the expansion history of the universe. All right, so in math, we would say that, okay, photons are traveling on these null geodesics, and therefore W space-time, that would be linking distances to the Hubble rate, or h, the rate of expansion. But what you should think of is that if you have some way of inferring distances in cosmology, that distance characterizes light travel time, and you measure redshifts from spectra, that characterizes the size of the universe at any given time, and that tells you what the expansion history of the universe is, the scale factor, giving you the size and the distance being a measure of look back time, essentially. And as everyone here I'm sure knows, there are two principal ways of inferring distance, and this cartoon example is how you would infer the distance to a car coming towards you. You would infer it because you have some intrinsic idea of how bright something is, which will be the supernova that discovered the accelerated expansion, or you have some idea of a length scale, the distance between these headlights will be the sound horizon in tests like the background acoustic oscillations and the microwave background. And if you know something about those intrinsic scales, then you infer from the 1 of R squared law the distance, and then you measure redshift. So as everyone knows, that's how the acceleration of expansion was discovered in supernovae. Supernovae are dimmer than expected in decelerating cosmology. And that means that h, this expansion rate, is more constant than expected. So again, it's the expansion that's accelerating, not the rate of expansion that's accelerating. H is in fact asymptoting towards a constant Hubble rate. And almost simultaneously at the time, so there was the option before, so it was long established that the matter density was low, so the options at the time were a cosmological constant or an open universe. And the microwave background supplied the other side of this story, which is having a standard ruler that told us that the universe was flat around the same time, and that was the convincing evidence for an accelerated expansion. So if you have a universe where h is going to a constant, the Friedmann equation would say that the energy density is going to a constant, so as the universe expands, instead of diluting the energy density, this is something that remains constant as the universe expands. That is, we're going to approach a de Sitter phase where we're dominated by a constant of nature. which, in the simplest possibility, would be the cosmological constant. So this is another joke. This is actually a deer in Narrow Park in Japan. And so I wouldn't say that it was unexpected. So from a phenomenology perspective, lambda was always an option. For decades it's been an option. And in fact, the matter density was known to be a poet at the time. So it was one of the two options. But if you're from a theoretical standpoint, this hits you like a deer in the headlights, which is the joke here. Because simple is not natural. So the simplest possibility is that it's consistent at least at the 2 sigma level. The cracks that I put on the first page are really tiny. That is, they're 2 sigma-like things that might be indicating something, but really it's beautifully consistent with the simplest possibility, which is just a pure constant, Einstein's cosmological constant. And in fact, particle physics provides such things in the vacuum energy, in zero-point energy with the particle side, and in the vacuum energy with our ground state. But, of course, as you also well know, this energy scale is way, way off the expectations of particle physics. So you would have to argue that all of these UV physics things, all of these things associated with energy scales of the particle physics scale, are canceling out things that are not related, not necessarily related to each other, like phase transitions and the vacuum energy associated with the phase transition and zero-point energy. They all have to be fine-tuned and cancel out to this at least 1 part in 10 to the 60, all to the energy scales of known, well-tested physics. And if you go all the way to a Planck scale, that's the 120 number. So it requires an extremely unnatural fine-tuning, which would disturb you as a theorist. And that it would hit the observational fact that we live in an accelerated universe hit theorists like that deer in the headlight as a discovery of an empirical fact of the universe. So now and even if you were thinking about just being a phenomenologist, it is still disturbing, right? Because the cosmological constant is a constant as the universe expands, matter and radiation are diluting. So this would be the only epoch where the matter density and the cosmological constant could be comparable if it is a true cosmological constant or the coincidence problem. All right, so now let's jump to the present. And I'll update you. I wanted to introduce those things because those are still the ways that we best test the accelerated expansion. And in fact, this tie-in from the molecular background side is one difference in how we're thinking about probing redshifts and distances today than when the discovery happened. That is, we have this strong tie-in to the early universe, and we'll talk a little bit more about the calibration of that standard ruler and what cracks might be. But it's sort of an inverse distance ladder. We're well tied at the high redshift end. We have observations of the same physical phenomena, which is acoustic oscillations in the early universe in the galaxy distribution, which are called acoustic oscillations. And those go all the way down to the redshifts where you measure the supernovae. And the name of the game now is in precision, which we'll see all of the observations of supernovae and which are the things you should ignore are actually the projections. Did I have to turn that to do this? Oh, it is on. Okay, it's just very lit. Right. These I stole from an EMOS figure, and they unkindly gave me a pixel image where I couldn't delete the projections, but you should mentally delete the projections. Those are not data. These are data, and the bands are predictions if the flat cosmological constant model is the correct model of the universe. The high redshift microwave background will tell you what you should see in the distance redshift relation, which are these bands with 1 and 2 sigma error bands here. And the rest are measurements of supernovae and baryonic acoustic oscillations. And you can see that supernovae have long achieved the precision of this level, and it's been a heroic effort to get systematics to the 1% level, as supernovae have been, but Castorides played a large part in that. And more recently, the baryon acoustic oscillations have also been getting down to the percent level precision, where systematics is the name of the game, and statistics no longer dominate the inferences. So that's the beautiful agreement, right? That's what you would expect if it were a pure cosmological constant, and the errors are reaching the percent level. All right, so how does this work? Since I don't think we've had a talk in the other features symposiums, we didn't talk much about the baryon acoustic oscillation. So let me remind you what that's based on and what the assumptions are there. That if we'll see that there are these tensions that you might think have something to do with dark energy, could we use those as clues to see what it might be beyond the cosmological constant? So I'll remind you that this comes from the also beautifully measured microwave background, which tells you that you have acoustic oscillations in the photon baryon fluid that are frozen in at recombination. And better yet, you can calibrate the physics. That is, it's a very simple linear system, and you know there are only two things that are important in calibrating how far sound can travel. That is, essentially, what's the age of the universe, and what's the sound speed of this fluid, or the photon-baryon ratio, and what's driving the expansion, what is the matter radiation content of the universe. And those are nicely encoded in the shapes of these peaks. So DAISY was John Karlstrom's experiment that first detected the third peak, and at that point we knew what the cold dark matter density is. We knew from Boomerang and Maximo what the photon-baryon density ratio was, which was a nice agreement with EBM predictions. And this supplied the final thing, which says that that pins down what we should see as the standard Bohr, and the rest is a consistency check that we could see. So this is the basis of things to do with VAO as well. The calibration of the distance sound can travel is based on knowing what the matter radiation density is and photon baryon density is. And once we do that, we also have consistency checks. So we have a check in this whole series that SPT first measured, but now is Planck data, predicting what you should see. And you can see that the red line is the prediction, and the data nicely do follow it. But as you probably know from back and forth on the archive, there are tensions in here. So this is where you might start looking for a crack. That is, when people split the data between this stuff and this stuff, there are minor tensions in this predicting this or this predicting that. And they don't quite agree at a level of about 2 sigma. So keep that in mind for what I want to say next, but let me just say how that then filters down to the rest of the predictions, and then I'll show you the tests of those predictions. So the bottom line when you're looking at these large tables of numbers is that the CMD is supplying the calibration of this sound horizon, and the thing that is the most important thing that quantifies that is how much dark matter density there is. And to the extent that that is measured precisely, which Planck in 2013 was this sort of level, and now it's better, tells you that you can do this angular diameter test of looking at a standard ruler and measuring the distance to this well-known redshift to about a quarter of that in accuracy. Which tells you also that in a flat-band CDM, you've specified all your parameters. That is, to the extent that you know what the matter density is, it's told you the precision for which you should see things like the Hubble constant today, which is in dimensionless units h. But not only that, it says that you know that at all redshifts, because that's really the only parameter left in flat-band CDM. So at all redshifts, you should have a prediction for what the expansion rate is, what distances as a function of redshifts are, as well as in a lambda CDM cosmology, where the only thing is a constant dark energy density, that defines all of structure formation, all of the growth of structure is now then predicted by the high redshift cosmology. Which means that looking to see whether these predictions are actually fulfilled is a great way of looking for cracks, right? That is a prediction, not a measurement. That tells you that if Lambdas was the explanation of the dark energy, you should see this. And one dramatic thing is that the CMB measures all of those energy densities at high redshift. If it weren't for the dark energy, what would H naught be? It would be 38-ish, 40-ish. And this difference between hat and the real H naught that one is measured is all the dark energy density. So that tells you that these things are directly measuring what the dark energy content is if you knew what everything else was by the high redshift measurements. And so you could try to quantify this in terms of parameterizing a deviation from the cosmological constant in the background by looking at the ratio of pressure to the energy density in the background, which is called the equation of state parameter. So let's jump to what Wendy told you about in her futures colloquium. So Planck makes a prediction for what you should have for H naught, and in fact, the most local stuff, ironically, is where you would expect the biggest fractional deviations. So if you weren't worried about errors and systematics, and I just asked the question, where would I go to see the biggest deviations from the lambda CDM cosmology? It would actually be the lowest redshift you can measure, which in the expansion rate is H naught. This is what it predicts. These are the measurements that Wendy showed you as compiled by Planck in 2013. And you can see that they favor higher values of H naught. That roughly is 2 sigma-ish value. So in terms of, could it be something about the dark energy? Well, I introduced the equation of state. So yes, if you change the equation of state, you change all those predictions, you can get something which is, let's say, a Hubble constant of 67 up to 74. This is just usual numbers. And of course, there are much larger, there are error bars that make it, so you don't really have to do this much. But if you did this, it would be a 10% shift from the prediction from lambda CDM to 74. And that sounds interesting, right? That sounds like, well, we measured something around here. If we make this much more precise, that might tell us that we're not in a cosmological constant universe. And in fact, the hints are, if you just took that alone, that it would tell you that. Well, what you'll notice from this curve is this is the deviation from a lambda CDM prediction of the Hubble rate as a function of redshift. It's predicting smaller deviations at higher redshift, but non-negligible. So if you reach the percent level precision at higher redshift, you can match something as a 10% effect at the lowest redshift. And as you saw, the Baron acoustic oscillations in supernovae have done that. So let's see how that works. This is a historical plot. You'll notice that I haven't changed this plot in many, many years. And I'm flashing this actually because a historical note is when we were starting to think about what you would do with Baron acoustic oscillations long, long ago. Our first thought, because this was 98, and the acceleration of expansion was just discovered, is this was the missing key. This was the test, right? H naught. You could show that H naught was consistent between these measurements, then you would be convinced that it was a cosmological constant. So if you measure Baron acoustic oscillations locally, that's exactly what you're measuring. So you measure in redshift space and angle in units, that would be H megaparsecs inverse, and you have a prediction from the sound waves in physical scales in megaparsecs inverse, and you would just adjust the observation, adjust the scale of the observations to the theory. That would tell you what the Hubble constant is, and that was actually what we wanted to do long ago with acoustic oscillations, is to get H naught right. I remember asking Wendy at a conference around here, well, if Baron acoustic oscillations won't be detected for many years, is it still going to be interesting to measure H0 to a few percent precision, given that this was long in the future. And I won't tell you what she answered me. But she answered, it can do better than 10% or something. But let me jump more to the modern standpoint. So in the modern standpoint, you're measuring it further out in redshift. That is, you're doing this more like a CMB test. And in transverse direction, you're doing an angular distance redshift test. That is, you know what the physical scale is. You measure the angular scale in the transverse modes. And you line these up again, and that tells you the angular distance is about redshift. And I'll remind you what the current measurements are. And now look at this percent level precision. So that deviation of 10% at the lowest redshifts does decrease, but you should still be able to see a significant, at the level of percents, deviation if that were the explanation. If I were just to change a constant equator state and make it match H0. And even more powerful is that you don't get just restricted to 2 dimensions in baryonic acoustic oscillations. You measure the full 3 dimensions. That is, you measure a set of modes both in the plane of the sky and in the radial direction. And in the radial direction, what you're doing is you're comparing the scale in redshift space to the physical scale. That is, you probe the expansion rate at that bud, and you do the same test and measure the expansion rate. Or in other words, when you're measuring a power spectrum, you measure the 2-dimensional power spectrum of transverse modes and parallel modes. And this is just an illustration of how you think about baryonic acoustic oscillations. There are rings in this space, and you have a known physical scale, and you can take a fiducial model, and then you adjust it until you get the right Hubble rate and the right angular diameter distance to that redshift. So in these measurements, you're measuring a power spectrum, but not just a power spectrum as a function of K. It's an anisotropy of the power spectrum, the monopole and quadrupole of the power spectrum. And this is the prediction that you should also see a deviation in the Hubble rate. And those are not quite as constraining yet, but you'll notice that this is also starting to become in tension with the explanation that it would just be some sort of smooth dark energy that just affects the background as an equation of state. But remember what the assumptions there was. The assumptions were that the background calibrated this ruler for you, and I said that there are tensions there as well. That is, how well you know that the physics of the earlier universe defined what this length scale was for you changes all of these inferences, including the BAO and including BAO that calibrate supernova going all the way down the inverse distance ladder. And that ties in with the next step. So the most incisive probes right now are these tests of the expansion history. But in a lambda CDM cosmology, and in fact, in a general cosmology where you think that most of the dark energy effects are in the background expansion, it also predicts what you should see for the growth of structure. So let me talk a little bit about this, because I'm going to generalize this at the end of the talk. But I'm going to tell you why this as an intermediate step is interesting. So only a cosmological constant is going to be spatially smooth in all frames. Right? So the universe is evolving, and if it were anything but a cosmological constant, something that depended on time, I could not tell you that in all frames I would have a smooth component of dark, spatially smooth component of dark energy, something that just affected the background. That is, inevitably I'm talking about things that would affect structures in the universe in a more direct way than just in background history. But if, just like in terms of thinking about collapsing objects, if you have a relativistic stresses in the dark energy, their gene scale can support the system of whatever this dark energy, mysterious dark energy component is, against gravitational collapse. So if you posit that the dark energy is something that only affects the background, what you're really saying is that the sound speed of the dark energy is comparable to light, that is comparable to the whole horizon in terms of the gene scale. And then, although the dark energy is not going to be completely spatially smooth and in Brownian cosmological constant, it is at least negligible compared with the dark matter. So it's something that you can ignore when you make even precise predictions for what you see in the dark matter side. Okay? And then I'm going to generalize this idea, which is the more complicated models where that is not a true statement. So in terms of observables, why I introduced the two-dimensional power spectra is that also in those measurements, you get a measurement of the growth of structure because you measure in redshift space. So the velocity fields give you an apparent enhancement of clustering for the radial modes versus the transverse modes, which is called the redshift space distortion. And those are beginning to become decisive as well. So this is essentially measuring the velocity field or the growth rate of structure, scale factor derivative of growth function of structure. And again, predictions of a flat lambda CDM model in the gray, and then just some arbitrary change in growth rates here, just to illustrate how things move if you're not lambda CDM, compared with the data. And you'll notice some of these, at least the ones that were early on, were predicting low values. Interesting, but rapidly developing, so this is the test of predictions of the growth rate. The well-established predictions, the more precise predictions, tests of the prediction, come from the cluster abundance. So this is something that became very interesting after the plot data set returned even more precise values of that matter density, better calibration of lambda CDM parameters, told you what you should expect to see in the abundance of rich clusters. And this, John talked a lot in his futures symposium. So this is back to 2013, the comparison of predictions for the lambda CDM cosmology versus the data for the abundance of clusters. And you'll notice that those are low, some of them were significantly low. And this, at the time, was a 3 sigma statistical discrepancy. Now, I say statistical because to do this sort of observation, you have to be able to measure what the mass of a cluster is. So in terms of the systematic error is how well you know the mass of these clusters. So if you shift by about 30% the mass of these clusters higher, then you would match the lambda CDM prediction. And since then, this is the 2015 comparison, you'll see that, well, you could get movement by different calibrations of masses. I'll talk a little bit about the lensing side of this, but you'll see that they're calibrated by weak lensing. And some of the recalibrations of masses of clusters will move you in the direction consistent, but some of the other ones that have come up, that one, measuring lensing by the microwave background itself, which has made dramatic progress in the last few years, to the point where the statistical errors are getting comparable to the lensing of galaxies measurements of masses. That's actually the most discrepant. So it all depends on what you think the calibration of the masses of clusters are. And as Andre would like to point out, even if you did shift the calibration of the masses, then you put problems in other places. That is, okay, you get agreement in abundance, but the baryon to dark matter fraction now be way off what used to be in it. Okay, great. So I'll remind you that these are calibrated mainly by weak lensing. That is, if you look at the shear distortion of background galaxies around things like clusters, got this nice tangential shear pattern. And you can also measure not associated with structure that's not associated with clusters, that is the weak lensing from large-scale structure, and that also measures the growth of structure. And that also is in tension with lambda CDM predictions. The CFHT data is also providing low amounts of structure compared with lambda CDM. So watch this space. It's going to be exciting with the DES data, and Josh will tell you a lot more about that in the next future symposium. This, one remarkable thing is how this is a cross correlation between SBT lensing, CMB lensing versus the DES lensing. And although this is not the most stringent limit yet, because it's just early days for DES, it's just amazing the progress. And, I'm especially impressed by the CMB stuff because that's something I was involved with 10 years ago. It's happened much better than I thought it would be. So great credit to John and the experimenters for making this happen. Okay, so let me summarize local cracks. So you have this high redshift inverse ladder, that is, we know the high redshift universe very well. We're making predictions assuming it's a cosmological constant. Are those predictions agreeing with observations? Well, not quite. The Hubble constant is a little bit higher in reality than measurements locally than they're predicted to be for that CDM. And the growth of structure is a little bit lower. So could this be new physics in the dark energy side or new astrophysics? That's unknown right now. That's something that I think KSP is sort of uniquely placed to resolve these things. As Wendy told you about, we have great expertise in H-naught. We have things that are developing, like Dan Holtz's sirens with gravitational wave measurements. And we have new ways of getting new versions of an old way of getting H-naught through strong lensing that Josh will probably tell you more about. As well as understanding the physics of clusters, the expertise here in trying to resolve those issues of mass calibration and ion fraction clusters. Watch this space. But what I should say is in those plots, those were going the opposite ways. So if it were just something in the background affecting the expansion rate, these two tensions are going in the opposite direction. So they don't indicate something like just changing the background expansion history. So if you were to look on the physics side of things to see what might explain this, what you have to do is break this consistency between growth, distance, and the high ratio standards that are calibrating things like paraacoustic oscillation. So in the last few minutes, I want to talk about those. So that is going beyond this smooth dark energy paradigm. What if these cracks really develop into big fissures in the structure of lambda CDM? What are our options there? I'll start out with this thing that, well, we have these measurements. We're inferring that it's some missing energy content of the universe. But it could be something else, right? It could be a very much more complicated dark sector than that. And this analogy is, well, we have in history examples of this where we measured very precisely the orbits of planets, and we look at these perturbations. One of them turned out to be physics. One of them turned out to be general relativity, changing the orbit of Mercury, the precession of Mercury. One of them turned out to be a missing energy density Pluto as a planet. So could the same thing be happening here? That is, could our inferences about acceleration really be some incomplete knowledge of the dark sector and how forces work in the dark sector? Okay, so let's continue that solar system analogy. There, what we can do is measure things in two ways. We can measure the orbits of planets, non-relativistic motion around the central mass of the sun, or the Newtonian potential and general relativity. That would be a time-timepiece. The metric and space curvature, relativistically moving things, would also experience the curvature of space. In gravitational lensing, that was the test of, that was one of the principal tests of general relativity. The same thing happens cosmologically. That is, the most incisive tests of gravity still reduce to this thing, which is essentially the space curvature per unit dynamical mass. And that's one of the things that you were trying to extract from the data to test dark energy. But another thing I should emphasize is, unlike the solar system, it's not quite that well condemned, because in the solar system we know the dominant mass of the sun, and we know a lot about the sun. Here we're talking about, if we're talking about dark energy as an unknown component of stress energy and something else as a modified force, there's an ambiguity here, because we don't know what the structure of this dark energy component is in terms of its stress energy structure. That means that you could think about this two ways. You could think about this as an exotic component of dark energy that produces the same phenomenology, or something that is modifying the forces. So, how do you want to think about this? There is this vast space of possibilities in the theory space. Well, one organizing principle is this so-called effective field theory, organizational principle. That is, you're trying to look, if you don't have any compelling model for dark energy, the UV physics of the microphysics of dark energy, what you might want to do is think about this as an effective theory. You want to think about everything that's consistent with homogeneity, spatial homogeneity, and isotropy. That is, what are the things that you could write down that are consistent with an unbroken translational invariance and a broken time direction, and so on. I'm not going to dwell on this on the particle physics side, but you can think of this as introducing this. That's why I have pi in the original diagram, Stuckelberg scalar. What I want to say is that that's one way of thinking why we're all talking about things like scalar extra degrees of freedom. That's something that is naturally consistent with homogeneity and isotropy. So if you think about all the possible interactions that you can have between the scalar sector and the tensor sector, that is a general scalar tensor theory of gravity, that gives you a framework for understanding what the possibilities are on the dark energy side. So how much time do I have? About 5 minutes? Okay, good. So say a bit about phenomenology there. So again, we're going to tie this into what you can observe. And what you can observe are these things associated with what I was showing you before, is how non-relativistic particles move versus relativistic things. That is, what's the space curvature per unit dynamical mass? This comes in the dark energy literature in different names, called the gravitational slip, or again, this degeneracy between thinking about this as a change in the force law versus an unknown, complicated component of dark energy. The same thing could be generated if your dark energy weren't just a simple energy density, but also had anisotropic stresses, and you could also generate a deviation between this unit space curvature per unit dynamical mass. The other thing that you look for is the relationship between these gravitational potentials and density fluctuation. That is, what is the effective Newton's constant in terms of defining forces and how structure grows. And the final thing is the tensor sector. So this is a general scalar tensor idea of thinking about dark energy. The gravitational wave propagation speed and damping rate as the universe expands would also be affected if you think about a general scalar tensor theory. So those are the observables, and I've listed this as sort of post-Friedman type descriptions, because just like in the solar system, you're doing post-Newtonian type measurements to test how well we understand gravity. This would be the same analog in cosmology that we're doing sort of the next step beyond the Friedman background. And this has been very productive in the last few years in terms of defining the linear theory of dark energy. Now we have some framework to understand what linear predictions are. And before I lose the joke entirely, one of the useful things about a framework like this is it allows you to look at what could go wrong. That is, ghosts, which are wrong sign kinetic terms, and negative energy states, if you runaway processes where you generate negative energy states and positive energy states. Those are very bad. And gradient instabilities where you have imaginary sound speeds, and you can think about the linear perturbation sector as this as a necessary condition, no ghosts, no gradient instabilities. Usually, benignly, there's a Ghostbuster picture in everyone's talk when I get to this point of what we're doing here. Even with my Japanese theme for the day, I think these are much more scary. And in my experience, Asian women are much more scary than dead white men. Here's a much more scary version of ghosts. And that's been very useful, thinking about what you end up with is general scalar tensor theories can be parameterized by 4 things in the background, 4 free functions of time, and that's sort of what you would want to constrain. There are various languages for how you phrase these things. Well, we know that that has to break down, right? If that continued on to small scales, that would violate our test gravity locally. So you know that if you were thinking about this as a complete picture of dark energy, you have to have something happen where nonlinear interactions in the dark sector are suppressing these effects on the local scales where you measure very precisely versus the cosmological scales, which we're only starting to measure very precisely. All right, I don't have time to go through this, but basically the idea is there's some sort of nonlinear interaction, and the various possibilities are what is the nonlinearity. And this is the scalar again. Is it a nonlinearity in the scalar itself, or in its gradient, or in its second derivatives? What I do want to emphasize is that although we don't have any one model that is compelling compared to Lambda CDM, by studying these things, we get pieces of a framework that might go into building a successful model. And one of the interesting things in the last decade or so has been how many times this has popped up. Interactions that involve the second derivatives or having a Galilean symmetry where gradients don't see this nonlinearity has popped up. It's in the next slide. I should say that Andre's student was the first person to simulate screening mechanisms in cosmology. Keep popping up, that is, all the way back in 39, Pierce-Pauli proposed deviations in gravity due to a mass, which gave you these differences in forces that could not be compatible with observations. So suppressing them with nonlinear actions was something Weinstein, it was 1973, talked about in terms of a massive gravity theory. And it popped up in a completely different place. That is when Denali, Gavadazzi, and Pradi were trying to explain acceleration with brain world cosmology. The small scale limit, or the decoupling limit of that theory, gave you that same mechanism, that same symmetry. And it's popped up again, well, it's constructed as a covariant of Galilean, but in these new classes of models, it's part of this parameter space that allows you screening and acceptable behavior on local scales. This is just some catalog of things all the way up to the present time about models of dark energy. So let me end sort of here. That is, in terms of parameterizing the future in the theory domain, it's completely open, right? So I will not lie to you. I will not say that there's any compelling alternative to a cosmological constant from the theory side at the moment. In particular, we don't have a solution to the original cosmological constant problem, that is this fine-tuning in the vacuum energy, and no compelling argument even for the new cosmological constant problem or the coincidence problem. Why this finite value? Why now? And it's not fully general, the description of thinking about this as a scalar tensor model. That is, if you're modifying dark energy this way, you usually do get a scalar, but that is not necessarily all you get, especially in that brain world example. As you get to the Hubble scale, you get different sorts of physics. You see extra dimensions, or you see additional modes, vector modes, for example. So it's also not even fully general as an EFT. What I do think is interesting is that by exploring these possibilities, we've certainly eliminated what can't work. There are lots of things that cannot work because of those two instabilities. And they do provide building blocks, and these which are assembled into toy models. One of a recent one which you can ask my student about, who's seen the trials and tribulations of massive gravity, is trying to assemble all of these ideas that we would like in a more compelling theory of dark energy into a possibility that was massive gravity. There were also all these problems that eliminate what can't work. So in the theory space, that story has led in many directions, and the story continues, including the work of my student, Pavel Malala. So let me end there with a view of the future in this sense. So we're looking for cracks now. The cracks could lead to observations that compel us to say that there's something else going on. There's something dynamical about the dark energy. And the framework for understanding on large scales is in place. That's thinking about this as a sphere tensor theory. And the great news is, in this diagram, lambda is being popped off by all of these that we're going to be deluged by data. And lambda CDM predicts what you should see in essentially all of these things. There are so many ways to falsify lambda CDM, versus the danger of the look elsewhere effect and 20 different ways of falsifying lambda CDM. We're certainly the 2 sigma falsification of lambda CDM. So be careful about that. We want a consistency test that says this is leading to a consistent picture. And on the survey side, I'm going to leave that to Josh in March. Josh will tell you about all these exciting things that are coming up.
And we're now going to let Rocky set up. But if there's a brief, compelling question for me, not one that will lead to a long discussion, you could ask U.S. Carlos.
So in this alternative, basic gravity alternative, wouldn't the graviton mass, the natural size, should be for a cover size?
Yes.
Wouldn't it be as puzzling as the cosmological constant size?
Yes. So
In
it's
your
not.
third hand.
We put that in by hand. So again, it doesn't explain that small amount.
Doesn't-
The hope is that you would get something that would be significantly natural.
The microphone is not working.
The hope is that you come up with a framework where there's some enhanced symmetry that's sort of that mass here and that X once you set it. That would be, I can't say that it's been fully realized.
Okay, thank you. We're going to shift gears just a little bit, and I'm going to speak about dark matter, in particular, what may happen in the future. Now, I think whether you're writing a paper, giving a colloquium, or even teaching a class, you should spend a minute or so telling your audience why they should listen and spend time, and why this is important. So for dark matter, I think it's kind of easy. Dark matter is most of the mass of the universe, which I think is kind of important. We'll never understand structure formation or anything much about cosmology without the inclusion of dark matter. So it's important not just to say dark matter's out there, but to understand the nature of dark matter. So according to the cosmologists, International Brotherhood of Cosmologists, I'm required to show a slide like this before every lecture. This is one reason you should care about dark matter. If you still don't care about dark matter, let me just warn you that the dinosaurs did not care about dark matter. And apparently the dinosaurs were hit by a dark matter particle that came in that killed the dinosaurs. So there's a lesson there, another reason you should care about dark matter. So in terms of the far future of dark matter, what is our goals? Our goals in this dark matter game. And I've divided it into goals for particle physics and goals for astrophysics. For particle physics, we want to understand the nature of dark matter and how it is embedded into a deeper theoretical framework. So if dark matter is a particle, we want to know more than just the mass, the spin, and the couplings. We want to know how dark matter fits into some how to embed it into a deeper theoretical framework. We want to know why dark matter exists, and we want to understand and be able to predict its contribution to the mass budget. Why is omega dark matter 0.2 or whatever it is? What is that value? Why is it that value? And on the astrophysics side, excuse me, we want to understand the role of dark matter in the evolution of the universe and in structure formation. Is dark matter completely cold? Is there only one dark matter component? Does dark matter have interactions that affect structure formation? Now, dark energy might have arisen in 1998, but dark matter, the idea that there's dark matter started a long time ago. There were papers written as early as 1919 or 1920 that tried to measure the local mass density, and they noticed that it was a little bit larger than one might expect based upon the luminosity measurements. A remarkable paper that really showed that was a paper of Jan Oort in 1932, and he came to the conclusion that our local stellar neighborhood is a little bit dim with a mass-to-light ratio of about 2 to 3, and the number that he found in 1932 is still a good number. In 1937, Fritz Zwicky measured the virial mass of galaxy clusters, and he discovered that they are really dark with a mass-to-light ratio of about 500. Again, our present value for this is very close to Zwicky's original value. Later, Rubin and Ford measured individual galaxy halos, and other people saw that they are also dark. And recently, very small observers, dwarf observers, have observed dwarf galaxies and find a remarkable mass-to-light ratio of about 3,000.
What
So-
was Oort's distance scale?
I'm sorry?
What was Oort's distance scale when he talks about local?
100 parsecs. Now, I think it's fair to say that the evidence of dark matter from the local neighborhood is not compelling. The first real compelling, you need a buck or something? The first really compelling evidence came from Zwicky, and he's credited, in fact, if you go to his birthplace in Varna, Bulgaria. He was Swiss, but he was born in Bulgaria. There's a plaque on his home that says, "In this home was born Fritz Zwicky, the astronomer who discovered neutron stars in the dark matter in the universe." Zwicky attended ETH in Zurich, and last year I was in Zurich for a couple of times, and I knew that he lived at, while he was at ETH, a student at 17 Spiegelgasse in Zurich. So in turn, we actually had dinner after my colloquium on Spiegelgasse, and I ran around to see whether there was a plaque on the home where Zwicky lived. So I run down the street and I see in the distance the home, and there's a plaque there. And I run up, but the plaque says, "In this home lived Vladimir Lenin." He lived in the same large apartment building next door to Zwicky at the same time Zwicky was a student. So Zwicky went on to discover dark matter, and Lenin went on to found the Beatles. It was really amazing who lived there. So I won't go through the evidence now that there is dark matter. It's compelling. Cluster dynamics is wiki measured. Galactic rotation curves, as Rubin and Ford and people, mass disadvantaged galaxies, gravitational lensing, nucleosynthesis, looking at X-ray cluster X-rays from cluster gas, CMB background radiation, structure formation, cluster collision. It's compelling that there is dark matter, and it's incumbent on us to try to understand it. Astronomy has made contributions to dark matter and can tell us more. First of all, astronomy tells us that dark matter exists. Thank you, astronomy. Astronomy has the ability of telling us the local dark matter phase space velocity distribution. This will be very important for direct detection. The local value of dark matter density, again important for direct detection. And then questions like, are they nearby dark matter subclumps? What is the background gamma ray emission from the galactic center? This will be an important background in indirect detection of dark matter. And astronomy can tell us the dark matter density profile very near the galactic center in dwarf spheroidal galaxies and in dark matter subclumps. Perhaps astronomy will be able to tell us if the dark matter is multi-component, like visible matter. If you look around at the small, insignificant amount of stuff that we do see in the universe, it's not in one species. It has a remarkable variety. Perhaps dark matter is multi-component also. Does dark matter have self-interactions? We know it interacts weakly with normal matter. Does it interact more strongly with itself? Does dark matter have normal gravitational interactions? Of course, if we had a complete particle theory containing dark matter, we could answer at least those last three questions. Over time, there have been many ideas for the nature of dark matter. So we look at a galaxy and we see there are missing pieces that we do not see. These missing pieces is the dark matter. What is the nature of dark matter? It has been proposed, and people have studied the fact that Einstein and Newton didn't have the last word. Either there's modified gravity, or people have even proposed modified Newtonian dynamics. In other words, that F is not equal to ma. The only evidence for modified Newtonian dynamics comes from a precision Swiss instrument. This is modified Newtonian dynamics. Velocity is equal to mass times acceleration. I'm not going to follow that idea. In the 1980s and the 1990s, it was very popular to consider the possibility that the dark matter consisted of something known as MACHOs, massive compact halo objects. And there were various ideas for these massive compact halo objects. One was there were big rocks, rocky rogue planets that are around in our galaxy. The other would be mass challenge stars. I'm not allowed to use dwarf stars now at universities. They have to be mass challenge stars. Or black holes. But at the end of the 90s, precision measurements in microlensing ruled out this possibility. And the possibility that's remaining, that's the most attractive possibility, is that the dark matter is an unknown particle species, a new species of elementary particles. Now, a question you could ask is, we have a lot of known particles, why can't the dark matter be one of the known particles? Well, what do we know about the dark matter? We know that it must be stable and massive and interact weakly. So if we look at the known particle species and say it must be stable, we can get rid of a lot of particles. If we say that dark matter must be massive, the force carriers are massless, so they cannot be the dark matter. And also the dark matter has to be sufficiently massive, massive enough, and so not completely believed by everyone, but most people feel that the neutrinos, the 3 neutrinos that we know, are not massive enough. And the dark matter has to interact weakly, so we can get rid of the particles that have strong or electromagnetic interactions, and nothing's left. So this comes to the very attractive conclusion that the dark particle must be beyond the standard model. Over the years, there have been hundreds of proposed models containing dark matter. I've taken this slide from a recent talk by Tim Tate, and this just gives you some broad ideas of some recent ideas. There's QCD axions that I'll talk about, stereoneutrinos, light force carriers, minimal supersymmetric standard model, supersymmetry in general, extra dimensions, little Higgs models. There are a lot of different ideas of dark matter, and a lot of different ideas for the origin of dark matter. These include that they arise from cosmological phase transitions, and an example of this would be axions, which have a mass of about 10 to the minus 15 GeV. Asymmetric relics, the idea that it is an asymmetry between a dark matter particle and a dark matter antiparticle in number density, and that determines the present abundance. In the simplest model, that mass would be about 6 GeV. Cold thermal relics, that will be the main subject of this talk, WIMPs have a mass of about 100 GeV, and gravitational production is another proposed origin of dark matter. These are WIMPsillas, and this would have a mass of about 10 to the 12 GeV. Another way of looking at the possible dark matter is there are thermal relics, or dark matter that results from the decay of or oscillation from thermal relics. And this includes sub-electron volt mass neutrinos. WIMPs exist. Neutrinos exist. They are around us. Stereoneutrinos, which would be warm dark matter, have a faster velocity, or cold dark matter, the lightest supersymmetric particle, or the lightest Kaluza-Klein particle. There are ideas of dark matter arising from Bose-Einstein condensates, axion mini-clusters, solitons, supermassive WIMPsillas. These come from phase transitions or inflation. These are non-thermal relics. So theorists have been hard at work for 30-some-odd years, limiting the possible mass of dark matter to 81 orders of magnitude, just to give the experimentalists some guidance, somewhere in that range. And we've given them guidance that the interaction strength should be somewhere between only gravitational and strongly interacting. Thank you very much for that. Now, what I'm going to follow through is, I think, the most compelling explanation now for dark matter, and that's not WIMPsillas. It would be cold thermal relics, and this is based upon a very simple idea that the dark matter was once in thermal equilibrium and remained in thermal equilibrium and then froze out of thermal equilibrium due to its interactions. So this is a simple graph that shows this possibility. This is a cold thermal relic, and if you look in the dictionary definition of a relic, it's an object of particular veneration. So there's a right name for this. This is a graph of the relative abundance of a particle species, say compared to photons, as a function of its mass over the temperature. At very high temperature, when the mass is irrelevant, it should be about as abundant as photons. And if the particle remains in local thermodynamic equilibrium, as the temperature drops below the mass, as m over t becomes larger than 1, its relative abundance will decrease as a Boltzmann factor. But because the particle has finite interaction strength, eventually it will freeze out of interaction, And where it freezes out of interaction determines the value of the dark matter density today. And as you increase the annihilation cross-section, it stays in equilibrium longer and freezes out with a lower abundance. So its abundance today depends upon its annihilation cross-section. Now, this is not a new idea. Again, this was proposed 39 years ago this May in a paper that I think started a lot of interest in particle cosmology. A paper that was a Fermilab preprint. Some of us remember these old, I don't know what color these are, yellow preprints. Later, I'll explain to the students what a preprint is. And it was a paper by Ben Lee and Steven Weinberg, and the title of it was Cosmological Lower Bound on Heavy Neutrino Masses. In this paper, they calculate the relic abundance of a fourth generation heavy neutrino, which they proposed at a mass in the GeV range, with an annihilation cross-section Fermi constant squared times the mass of the neutrino squared. And they have a graph in their paper that's essentially the graph that everyone uses today. It's interesting that this paper, which I believe was so influential, was modified by an incorrect experimental result. Maybe some of you, some of our senior particle physics colleagues remember the high Y anomaly. I see Jim Pilcher smiling. You weren't on that experiment, were you? No. It's also a model that uses an effective field theory, and this model was excluded just a few years later by direct detection experiments and by left neutrino counting, but still I think it started the whole ball rolling. Also in the paper is an equation, that's the Boltzmann equation, describing the evolution of the number density of a particle species, and this sigma v is the non-relativistic annihilation cross-section, the thermal average of that times the molar flux. And you can solve this simple differential equation and find the final value of omega h squared is 0.11 or 0.12, the value we think it is today, times 1 over the annihilation cross-section measured in units of 10 to the minus 36 centimeters squared. So again, as the cross-section is larger and larger, as it becomes more and more strongly interacting, omega is smaller. If you want it to be the correct abundance to be dark matter, it has to have an annihilation cross-section of about 10 to the minus 36 centimeters squared. Now the calculation's not so clean, and I'll hit on some of these ideas later. But an interesting thing, if you look at the cross-section of 10 to the minus 36 centimeters squared, just write that as alpha squared over 150 GeV squared, and 150 GeV is the weak scale. Therefore, if the cold thermal relic is dark matter, it has to have a mass someplace around the weak scale. And this is the origin of the term WIMP, weakly interacting massive particle. And I'd like to give a shout out to Mike Turner, who came up with the word WIMP to describe cold thermal relic. I thought I'd show an image of Mike. The only image I could find of Mike is this one. And this, of course, now you understand Turner's famous quote. I have to get the rest of it. So the fact that you want a particle that has weak scale interactions is often called the WIMP miracle. I think this is a terrible phrase. We shouldn't be talking about miracles in science. What is a miracle? You know, it is an extraordinary event manifesting divine intervention in human affairs. Does that have anything to do with dark matter? I think a better definition of it is something from Wikipedia, something that's often used to give an impression of great and unusual value in a trivial context. Right, miracle wheel. So the interesting thing about dark matter is that they have to interact with standard model particles, and the relic abundance is determined by the annihilation cross-section of two WIMPs producing standard model particles. So this determines the relic abundance. This same interaction we will see will be important for indirect detection of WIMPs today, the annihilation of WIMPs in the present universe, and we can do a little bit better than that. This cartoon here is really a cartoon Feynman diagram. So here's a cartoon Feynman, and the cartoon Feynman will tell us that if this is the diagram, if it's a Feynman diagram, we can do things with it. We can read it in this direction by reversing some arrows, and it also predicts that a WIMP should scatter with the standard model particle, and we'll take advantage of this in direct detection. Feynman would also say that we can read the diagram in the other direction, and it predicts that standard model particles could interact and produce WIMP pairs. And we're going to take advantage of this crossing to try to look for evidence for the WIMPs from indirect detection, direct detection, and collider production. Now, so far I haven't said anything about the interactions of the WIMPs, how it fits into some larger framework, and I think there are two opposite views we can take. And this would be whether the WIMP is a social or a maverick species. Is dark matter social or is it a maverick? So here's an illustration of a social WIMP. It has a lot of friends. It's friended by many like mass particles. It pals around with new unwimpy particles. It's part of a larger theoretical framework. It would be a top-down description. I'll give you some theory, and the theory will contain a WIMP. Generally, this would be a UV complete theory, and the way you would look for the WIMP is by finding its friends. And an example of this would be supersymmetry. Or it could be that the WIMP is a maverick particle. It's all by itself. It's not friended by any new particles. There are no any unwimpy pals are beyond our reach. The theory framework is don't ask, don't tell what the fundamental theory is. It's a bottom-up theory. Generally, it's not UV complete. Effective field theory is used. You would find the WIMP through discovering what is not seen. And an example of this would be the discovery of the theory of neutrinos before the Weinberg-Salam model. So let's look at socialist WIMPs from supersymmetry. In supersymmetry, for every particle, there is a superpartner. And in supersymmetry, the Higgs sector cannot contain just one lonely Higgs, but has 4 Higgs particles. And there are superpartners for every quark. There's a squark, for a lepton, there's a slepton, photon, etc. These all have supersymmetric particles. This was developed in the early 70s, and the experimental evidence has never been stronger that supersymmetry exists. Every known particle has an undiscovered superpartner. The superpartners are massive. The lightest superpartner should be stable. And in many realizations, the lightest superpartner is weakly interacting and is a candidate WIMP. So this is an idea of the social WIMP. Now, or if we dig a little bit deeper in supersymmetry, for supersymmetric WIMPs or SWIMPs, there are many possibilities: gravitinos, neutrinos, axinos. The one I will spend almost all the time on is a neutralino. And the lightest neutralino is a linear combination of SUSY partners of the photon, the Z, and the Higgs bosons. The mass and Higgsino fraction of the lightest supersymmetric particle depend upon about 100 SUSY parameters. So people reduce this to a manageable number of parameters by picking some particular model, phenomenological, MSSM, constraining, M subra, etc. There are many possible processes and diagrams that contribute to annihilation, and there are many channels, and there are various possible annihilation channels of the WIMP, of the neutralino. One thing I would note is annihilation into fermion pairs is proportional to the fermion mass. We'll see where that may enter in indirect detection. I'll also note that there's no, at least at lowest order, no two-body final state with a photon. That will also be important for indirect detection. LHC and other experiments have pushed the SUSY scale high, which leads to a low cross-section, which leads to too large of a value of omega H squared unless there's some chicanery to increase the annihilation cross-section. And there are industries that have a type of SUSY known as focus point SUSY, where the neutralino has a large xeno component, large annihilation cross-section into W pairs. Resonant annihilation, where the neutralino annihilation goes through a pseudoscalar Higgs A, and the mass of this is approximately twice the mass of the neutralino, so at low, in the non-relativistic limit, it would be a resonant enhancement. Or there's an idea of co-annihilation, where there's another particle that interacts more strongly than the neutralino that it can annihilate with, and has a mass a little bit larger than the neutralino. So for supersymmetric neutralinos, choose a model framework to reduce from about 100 parameters, require a consistent low energy model with a neutralino dark matter candidate that satisfies all experimental constraints. The low energy annihilation cross-section depends upon neutralino composition, mass, and couplings, and possibly other masses, which in turn depends upon all these SUSY parameters. Generally, the annihilation cross-section times the velocity will have a part that's independent of the velocity, and a part in the non-relativistic limit, and a part that is velocity suppressed. It's true that SUSY dark matter phenomenology is very interesting and very rich. Very interesting and very rich is another way of saying that the SUSY dark matter relationship is complicated. And whether you like this or dislike this is a matter of taste. On the opposite side, there's effective field theory. Where the WIMP is the only state accessible to experiments, the other states are too massive. And if the other states that the WIMP interacts with to connect with standard model particles is very massive, then this can be reduced to a contact interaction with a coupling constant lambda, like a Fermi constant, which is G squared over the mass of W squared, the mass of this intermediate particle squared. Many theories have common low energy behavior where the mediating particles are heavy compared to energies involved. The EFT is not, effective field theory is not as desirable as a UV complete theory. One example of a effective field theory is just to assume that the dark matter is a fermion that interacts with quarks. And there are possible interactions where, it's just 1 over lambda squared, or if this is certain types of interaction where there's minimal flavor violation required, it would be 1 over lambda cubed with an interaction that's proportional to the mass of the quark. Okay, so for maverick WIMPs to calculate the annihilation cross-section in the present abundance, that determines lambda. And if you look at their various forms for the effective field theory operator, and the annihilation cross-section at low energy can have a term that's independent of velocity and a term that's velocity suppressed, and whether it's suppressed or unsuppressed depends upon the structure of the operator. About 31 years ago, Goodman and Witten wrote a paper pointing out that if the dark matter is a WIMP, it's possible to detect it in low sensitivity experiments. So we are sitting someplace in the galaxy here, surrounded by a sea of WIMPs. The WIMPs are passing through. And what would the interaction of a WIMP passing through a detector depend upon? It depends upon the local WIMP phase space density. It's usual to assume that the local dark matter phase space density is about, number density, energy density is about 0.4 GeV per cubic centimeter. Perhaps there are subclumps around or streams, but this is the usual assumption. And it's usually assumed that the local phase space velocity distribution is Maxwellian with an RMS velocity of about 220 kilometers per second. This is probably the first approximation of good description. This is the result of a paper that does an n-body simulation and has many realizations of what the local dark matter density would be. And the blue lines here show the 1 and 2 sigma variations, and the red line, the red curve, is the average, and the dotted line is the fit to the Maxwellian distribution described there. See, it fits pretty well, although maybe not at low energies, it could be something, or maybe at high velocity it could be off a bit. The type of interaction, whether it's spin-dependent or spin-independent, is important. For axial vector interactions, it depends upon the spin of the nucleus. It's a spin-dependent interaction. And the question is whether it has the same coupling to protons and neutrons. If it's a scalar interaction, there's a coefficient describing the coupling to neutrons and in a nucleus, and the coefficient describing the coupling to protons. And just graphing this, if Fn over Fp is not equal to 1, you can have suppressions for different nuclei, different target nuclei. Okay, so the idea of the direct detection is a WIMP comes in, hits the nucleus, and leads to a nuclear recoil of a certain energy, and you can simply write down the rate for this to happen, the differential rate, as a function of the recoil energy, and it depends upon the phase space distribution. There's a minimum velocity to give a particular recoil energy. And typically the recoil energies are a few to a few dozen keV, and exactly what this would be depends upon astrophysics, determining the local WIMP density and the phase space distribution, particle physics, depending upon the mass of the WIMP, and how the cross-section changes with recoil energy, and their experimental handles, the detector mass, the nuclear targets, the mass of the nucleus, and the spin of the nucleus, the threshold energy in the detector, and how, what d sigma dr would be. The first experiment to put limits on WIMPs was in 1987, 28 years ago this coming May, and their result was a few times 10 to the minus 36 or a few times 10 to the minus 37. There's been a lot of experiments since then. Here's some of them that Chicago has been involved in. The COOP experiment, this is Mike Crisler at Fermilab, wearing a helmet because he knows what happened to the dinosaurs. He's protecting himself from WIMPs. CDMS, PICO, Cogent. This is the best photo of Warren Kolar that I've ever seen right here. And Xenon that Luca Grandi is involved in. There's probably 24 experiments around the world. For Maverick WIMPs, the scattering of a dark matter particle with a proton or a standard model particle can be spin independent or spin dependent, or many interactions are suppressed by velocity or momentum transfer. So direct detection experiments cannot access every possible operator. This is a compilation that Michael Faraday put together of spin-independent scattering, what the limits are today. The sum of the limits are shown by the green shaded region and the various experiments that contribute to it. And the proposed future experiments are shown in these dotted lines. And there is a floor here that is the effective cross-section, where below this you would have to worry about neutrino scattering, neutrinos from the sun, or the neutrino background from the diffuse neutrino background from supernovae and that have occurred over the history. So going below this dashed line would be extremely difficult, and you see we're going down to that. Proposals are approaching that. And it's remarkable if you look at the values of the cross sections here. Today it's around 10 to the minus 46. Down here it's about 10 to the minus 49. There's new vocabulary you have to learn. We're familiar with picobarns and femtobarns, and particle physicists working at LHC are now talking about attobarns. Here it's septobarns is about what the limit is today. And down here at 10 to the minus 48, it's a yoctobarn. Going down 3 orders of magnitude below that, what would it be? I don't know, because I can't find in any book what is below 10 to the minus 48 square centimeters. What's below yocto? What's below 10 to the minus 24? If anybody knows, please let me know. For spin-dependent scattering, the limits are not as good, but they're still going down in the future. For instance, in PICO, one of Juan Pilar's experiments, down to about 10 to the minus 42 centimeters squared. How does this compare with expectations from models? Well, in the effective field theory approach for minimal flavor violations, scalar interactions, this blue line is the prediction, and experiments today have ruled out up to about 200 or so GeV for the mass. For for axial vector interactions, it will be a spin-dependent interaction. The black line is the prediction, and you see it's not really restrictive yet, but eventually it will get down to about a TeV, and eventually in the future, these experiments for spin-independent scatterings will get down to about a TeV. What about supersymmetric WIMPs and direct detection? Well, there's a possibility of spin-independent scalar-type interactions or spin-dependent axial vector interactions. This ratio depends upon the model parameters. The cross-section depends upon model parameters and can vary by many, many orders of magnitude. Again, the relationship status is complicated. This is one recent compilation of a prediction of a phenomenological minimal supersymmetric standard model with 10 parameters with LHC limits, and this is 1 and 2 sigma contours of what's predicted. And you see, obviously, it's just below the experimental limit. So if you experimentals would just work a little harder and push it down 2 orders of magnitude, there's a great discovery there for you, unless you could be unlucky and the cross-section should be down, or could be down around 10 to the minus 50 centimeters squared. So what's the present situation for direct detection? Maverick WIMPs, the vector couplings are excluded in the range 10 GeV to 2 TeV. Scalar couplings are excluded in the range 10 GeV to 200 GeV. Axial and tensor couplings are spin-dependent, and there are weak or no limits. Pseudoscalar couplings are velocity suppressed, there are no limits. For supersymmetric WIMPs, any limits are very model dependent, direct detection limits are constraining, and the LHC is pushing SUSY scale high, pushing to higher mass SWIPs. In the future, the thing to do is clear. You have some excluded regions, supersized experiments to push this down, and to have new techniques to push it down in the better limits in the low mass region. For the future of direct detection, the path is clear, at least to me. Again, our goal is to discover a WIMP or kill a 39-year-old idea. We should push spin-independent limits down to the neutrino background, which is no more than 2 orders of magnitude below present proposed experiments. There's a lot of white space to spin-dependent limit. Push the sensitivity to low WIMP mass, which may take new techniques. If you see a signal, look for seasonal variations, look for different target nuclei, directional sensitivity. If you don't see a signal in direct detection, think beyond nuclear recoil or start working on 21 centimeter astrophysics. Now let me turn to indirect detection. This again is not a new idea. There was a first paper I know about it was 35 years ago, and it pointed out that if the annihilation cross-section times the velocity is 10 to the minus 36 centimeters squared for dark matter, that's about 3 times 10 to the minus 26 centimeter cubed per second. And if you have dark matter in the galactic center, for instance, it could be annihilating, producing a signal that you can see. The idea is that WIMPs in the galactic center, dwarf spheroidal dark matter clumps in the sun, come together, annihilate, producing high-energy quarks, which end up fragmenting and decaying to producing particles that you would see, gamma rays, positrons, electrons. It can produce leptons, which can produce neutrinos that you could see, producing bosons. So the things you would see would be positrons, electrons, neutrinos, antiprotons, and protons. So we're sitting someplace in the galaxy here, and dark matter is annihilating in the galactic center, in galactic subclubs, in dwarf galaxies around us, and it would produce a flux of even photons and neutrinos, and whatever we want to see, that depends upon the differential with regard to energy, what the branching ratio is to the number of photons and neutrinos, the annihilation cross-section, and an integral over the line of sight over some angular region of interest of the density squared, rho squared over the mass of the WIMP squared. And what to look for, there are things we can look for. Charged particles are easy to detect, but there are astronomical backgrounds, and charged particles are bent by magnetic fields, so we don't know their origin. Looking for continuum photons or neutrinos, the photons are easier to detect, but there are astronomical backgrounds, neutrinos are hard to detect, and often have the dominant annihilation product. The best, easiest thing to look for, or the golden detection channel, is a mono-energetic photon line. There should be a low background or probably a low signal. Where do you look? Galactic center, you know where to look. It should have the largest signal and but also the largest backgrounds. Look at nearby subclumps of dark matter. There should be very clean, no baryons, but you don't know where they are. The signal's down by a factor of a few hundred to 1,000. You can also look at dwarf spheroidal galaxies. We know where to look. There's about 20 of them around us. This should also be clean. There are very few baryons, but the signal's down by about another factor of 1,000. There are experiments all over the world and in space in inhospitable places like Namibia and Arizona that's looking for the galactic center or places for the evidence of dark matter annihilation. And if it's calculating the annihilation products and the rates is rather straightforward for maverick WIMPs. Omega A squared tells you what the coupling is, and some of the interactions are velocity dependent. And unlike the early universe where V squared is just a few tenths, today the velocities are about 10 to the minus 3, so this would be a very large suppression. You would not be able to see these types of operators, but some of the operators are unsuppressed, and you should be able to see the annihilation. And it's interesting, if you combine this with the scattering cross-section, the direct detection information, you see that some operators you would not see in indirect detection but you would see spin-independent scatterings. Some you would see spin-dependent and not see an indirect signal. And if you put these together, looking at maverick WIMPs and saying what the signal or the lack of the signal is in direct and indirect detection, the combination of both pieces of information can signal out particular operators. For instance, if you would see direct spin-independent interactions and also detected in indirect detection, the only possibility is a vector-vector type interaction for the WIMP fermion operators. And it's a little bit more complicated if you don't see it in direct, but see it in indirect. And if you don't see anything, then it really pins down what the operator would be. And again, for supersymmetric WIMPs, the indirect detection relationship with supersymmetric WIMPs, some have velocity independent, some are velocity suppressed. The relative size depends upon model parameters. There are many possible final states, many possible diagrams. Branching fraction depend upon model diagrams. I will point out that the annihilation of fermions is proportional to the mass of the fermion squared, and there's no photon lines that you would see. So in general, again, for supersymmetry, the relationship is complicated. Now, I showed some limits for direct detection. Let me show you an example of an indirect detection analysis. And this started with the work of Goodenough and Hooper, and has continued on with many people contributing to it. And in this particular analysis, it's looking at gamma rays. They start with the Fermi public data and tools, pick a search region of interest, in this case around the galactic center, remove point sources and model and remove every non-dark matter astrophysical sources, and fit the gamma ray excess, if any, to cross-section and annihilation channels. So this is the region of interest around the galactic center. Something's masked out. And this was a recent analysis by Calore, Couloris, and Venegar. And they fit the excess to various models, a broken power law, a power law with an exponential cutoff, dark matter annihilation to BB bar, dark matter annihilation to tau plus, tau minus. And broken power law gives an excellent fit. Annihilation into BB bar would have a mass of around 49 GeV with a cross-section in the range that one would expect. It has a very good chi-squared per degree of freedom. CC bar also has, for the annihilation channel, also has an acceptable chi-square. Tau plus, tau minus is a little bit difficult to see. So again, the path is clear. Discover a WIMP or kill a 39-year-old idea. There is an overwhelmingly statistically significant gamma ray excess from the galactic center. Why aren't we all as excited as Dan Hooper? Well, it's because we worry, well, Dan does also, it's because of the existence, I think he does. Do you, Dan? Of possible background contaminations, is it thousands of millisecond pulsars? There could be background. We have to have a better astrophysical understanding of the galactic center, a better understanding of the dark matter density profile, and better observations. Gamma ray observations, in this case, with better angular resolution to resolve background sources, remove emission correlated with gas. Better spectral resolution would also be helpful. A larger collecting area would allow us to look for signal elsewhere, like stacking dwarfs. And ground observations like CTA would teach us a lot about background. So there's a real future direction there. Finally, in the -3 minutes remaining, I'll say something about looking for WIMPs at the LHC. My friends who are experimentalists at LHCs would say that looking for new particles is like looking for a needle in a haystack. Looking for dark matter is looking for an invisible needle in a haystack. If you just take the maverick limit, the contact limit interaction, The cross-section will be the same, the production cross-section of WIMPs would be the same for all operators. But if you have quark, anti-quark collision producing a final state containing only WIMPs, looking for nothing is difficult, but it's possible that in this process there's initial state radiation producing a jet of particles, and the final state that you would look for would be an energetic jet of particles unbalanced in momentum. So you look for monojets. Monojets are nature's garbage can. Everything, every idea in every new model would produce monojets. There's also monophotons, mono-Zs, inclusive B-jets. This standard model background is extremely well modeled and measured and understood. The neutrino background can be removed. Again, the couplings are irrelevant in the relativistic limit, and the thing to worry about is the validity of effective field theory at the energies of the LHC. For supersymmetric particles, the most popular is the neutralino. Gluinos, quarks, and charginos will be discovered before a neutralino. The analysis is model dependent. The LHC is chewing away at the allowed region for low energy supersymmetry. You can, supersymmetry, people can wiggle out, squiggle out of any limits, but it's getting harder, and it's not time to throw in the Tawalino yet. Stay tuned for results from the 13 TeV run from LHC that's just starting. Eventually, we'll see a WIMP in missing energy signals, but the first thing we will see will be the gluinos and squarks. What is the future of collider searches? The LHC has just started running at 13 TeV. Eventually, they already have accumulated a tremendous amount of data. They'll accumulate an even more tremendous amount of data. If dark matter is a SUSY relic, some indication of SUSY will be discovered at the LHC. The search strategies are well developed. If dark matter is a maverick particle, the only hope is missing energy searches, most effective for low masses, and there's no guarantee that the model is valid at LHC energy. Okay, so to conclude, I haven't mentioned the possibility that dark matter, well, I haven't gone into the possibility that dark matter is not a WIMP. There are many other possibilities: axions, asymmetric dark matter, stereoneutrino dark matter. For instance, a 7 keV stereoneutrino producing a 3.5 keV gamma ray line in the decay of the stereoneutrino to an active neutrino plus a photon, which may or may not be observed by XMM, Newton, Chandra, etc. An axino, self-interacting dark matter, inelastic dark matter, cue balls or other solitonic dark matter, quark nuggets, hidden sector dark matter, or even a himself. Okay, so last slide, what is the future? Second to last slide, what is the future? We are in the 8th decade of dark matter, going back to the 1930s when it was first seen astrophysically. The 2010s is the decade of the WIMP. LHC is running in this decade. Direct detection experiments are reaching into the signal where we would really expect to see, reaching down the cross-section where we really expect to see a signal. Indirect detection is really sensitive. And we have to run the idea of the WIMP to ground. The cold thermal relic hypotheses will be tested in this decade. 5 years ago, I had a terrible concern that at the start of 2016, we would have compelling evidence from indirect detection, direct detection, and LHC that didn't quite fit together. That concern has proved groundless. WIMPs may be more complicated than discussed. My prediction is we will know the answer before a century of dark matter, so before 1937, before 2037. Dark matter discovery will be unanticipated. Exactly how it's discovered will be unanticipated. Dark matter will turn out to be none of the above. It will be something different than we have imagined. Dark matter will be multi-component, and dark matter will be only part of the dark sector. So in this talk, I hope I've convinced you how exciting it would be to detect dark matter. And I'll just close with the gratuitous photo of Donald Trump and just point out that detection of dark matter would be huge. Thank you.
Okay, thanks to the two of you. Now let's, why don't you each bring a chair up here? Because I know you must be tired. Okay. Questions? Comments?
Your predictions of dark matter. So there were currently
I'm sorry?
going back to sort of addressing the predictions of dark matter. So if I remember correctly, the plot of the direct detection was spin dependent. There was no lower limit from the neutrino bit rates of keep going down multiplies. So if we hit the lower limit with the spin independent interactions, do you think it makes sense to continue going, or should we basically abandon direct detection and really focus on the other methods?
I think the generation beyond the generation being built now will hit the neutrino floor. I mean, that's the target. I don't think there's any compelling reason to push below that. It's really difficult. You would have to have directional detection to make sure it's not coming from the sun or some seasonal variation. For spin independent, there's still several orders, I'm sorry, for spin dependent intelligence, there's still several orders of magnitude that you can go down, and that's where the directions go. So there's a lot of white space left for spin dependent interactions. There's not a lot of white space left for spin independent interactions.
Great. Nicole,
Hi, so
welcome Nicole. Nicole
Thank you.
is a new fellow, and she's finally here, and now she's going to leave to go to the South Pole. But ask a question before you go to the South Pole.
Okay, this is more of a comment than a question. There is a lot of research going on currently, both in the theoretical side and in the experimental side, looking at, well, I can talk about direct detection because that was my graduate work. I don't know so much about indirect detection, but looking at the velocity suppressed and momentum suppressed operators. There was a paper published by Super CDMS in March 2015 that addresses this, and they were able to set limits on a lot of these operators. And my dissertation work was actually to investigate these same operators for LUX, for the Large Underground Xenon Experiment. And we will be putting out limits on these in the spring or early summer as well.
Good. Thank you for the comment. I'm aware of that. And when are you going to the South Pole?
On Monday.
Because Michael Federke and I, a graduate student in physics, are working on that very problem right now.
We should chat then offline. That would be good.
How long will you be at the South Pole?
A month.
And then she's going to give us a colloquium on the results from LUX, right?
Yes.
John,
Is there anything that's sensitive to the mass of the WIMP in the way of structure formation? Let's take the range from 100 GeV to a TeV or more. And the structure formation or any of the cosmological observables respond to that mass difference?
Once the WIMP is cold, then whether it has a mass of 10 GeV or a gram doesn't really matter.
You could have for very small things.
Right.
Scott,
So Wayne, since dark energy models also have extra fields, do you have in your mind a technical formal definition, the difference between dark energy models and modified gravity?
Yeah, in fact, I was talking, this might be a question for Austin, we just read a very nice review of former student that I thought he did. So we were just debating this yesterday about, so one way of doing it is to think about what it does on the view, but it's also, you can think of this as modified gravity is things that have universal couplings and also violate the strong rules principle. And you can tell me more about that.
Jim.
Let's see, I wonder, are there any astrophysical, is there any astrophysical evidence that dark matter interacts with ordinary matter other than gravitational? Because obviously the collider experiments, the direct detection and indirect detection all depend on interaction with ordinary matter by something that's not gravitational.
In general, there's no astrophysical or cosmological evidence for that. If the dark matter is a cold thermal relic, then it must interact with standard model particles, but it could be something other than a cold thermal relic. So it may not interact, the ultimate nightmare is that it has only gravitational interactions with normal matter. That cannot be excluded.
So I'm going to interject a provocative question for Rocky, because I know you're a fan of H.L. Mencken. And he's famous for saying for every complicated problem, there is a simple, elegant, and wrong solution. And you've told us about the 39-year-old idea of a WIMP, and talked mainly about the future in terms of that 39-year-old idea. You listed a whole menu of other possibilities, and right near the bottom, right next to WIMPzilla's, was dark sector, which is the idea that things are more complicated. And I was surprised she didn't say more words about the dark sector. And just to sex this up a little bit, if we remember the history of the universe, it started with just atoms, and then we had photons, and then we had neutrinos, and then we had, actually didn't mention that we already have two kinds of dark matter. We have neutrinos and we have cold dark matter. And so how come that idea that it's more complicated than this simple idea of the WIMP didn't get, tell us your opinion of that idea.
I agree with you as usual. I think we will discover that there will be a dark sector and that dark matter will be multi-component and it will be more complicated than we imagine today. However, let's do the simple things first, and pursuing the idea that it's a WIMP, I think within this decade we can close out that possibility and turn to other possibilities to close out. And the most attractive possibilities, whether they're true or not, would be the possibilities that can be experimentally verified. But again, I think I mentioned in the last, or second to last, the pre-Trump slide, that I think dark matter will end up being none of the above. It will be something more complicated, it will be multi-component, and nature has a way of surprising us.
Great. Oh, when you're close enough to give you the microphone.
So, a related question, in terms of dark energy, maybe Lee first, and maybe you want to talk to also, but before the discovery of the acceleration, the Hawking was really at a point where something was wrong. So if there were two sigma cracks in that too, and then the discovery of the acceleration, we press the mercury back on that too. Pretty much consensus of just standard of one log. But for the reason you pointed out, everybody's obligatory slide that show the orders of magnitude and the why now question. Can you speculate? Suppose the current data are consistent with the standard lens model, but data have sometimes of two sigma effects go away. So if it isn't dark energy, we can speculate on it might be.
It isn't a long So I should say, yes, their current data is consistent with a cosmological constant. So what you want to see is that some prediction is consistently failing. And for example, the growth of structure would be in that class. There are several lines of observational lines where the growth of structure is off. But of course, there's
value shifted.
between W9 and clock. So actually, we can all agree that W9
Could you keep the microphone close to your mouth?
So first we would like to see that there is some evidence that is really consistent, cross-checked, calibrated, all of the systematics, various things being independent, which is not true of things like BAO is services. BAO is relying on its distance scale. So if it is something like that, and you see a violation of consistency between the expansion rate and the growth rate, that would be a good indication that there is something interesting for sector that don't sector. So that would be a new direction. So we're certainly hoping that that is the future.
So what Wayne is illustrating is that the correct answer to any question that Wendy asked is more precise measurements of H0.
So I want to go back to Wayne on this one, because one thing that you didn't mention, there is a part of the United States, better known as the left coast, where your first slide about lambda and the tyranny of lambda, and all we get is lambda, and we don't understand it. The left coast would say, that's not a bug, that's a feature. This is solved. This is evidence for the landscape of string theory and maybe even the multiverse. I don't even think, I mean, at least I found the dark sector hidden on one of your last slides, just above the WIMPzilla. But I didn't hear you say anything about the landscape of string theory and the fact that some people think this has been solved.
It's my biggest fear, as I was still in the future. And it is a possibility. I certainly hope that is not the future, because there's not much more that we can say about that. We can distinguish it from multiple cluster. So going down in the observational space for verifying the numbers, and I hope that there's some ways about that. It is a possibility.
Great. More questions from the more provocative Nicole. I didn't mention Nicole's last name was Larson, and her thesis had to do with the results of Lux, and she's giving us this colloquium. When is it? The day after you get back from South Pole.
Pretty much, yeah.
Yeah.
The 17th of February, assuming everything goes well and I'm stranded. My question is going back to dark matter and all of the different candidates that there could be, the axions, the WIMPs, the WIMPzillas, and all of those. And what I was wondering is, are there ways to use cosmological probes to distinguish between those? Like, could you tell a WIMP from an axion by looking at large-scale structure formation or something along those lines, rather than just like trying to figure out which one is which in a laboratory?
So maybe I can you hear me in the back? Maybe I can answer without the microphone. There are handles that you have. One is how is the WIMP or the dark matter completely cold if it's a particle? That would point to warm dark. If it's not, it could be warm dark matter, or maybe there's a component of hot dark matter too. So it could point to something that's different than a relic WIMP, a cold relic. You can also, and there are various handles you can do, looking at structure on small scales in Lyman alpha clouds and things like that. Could give us information about that. There's also information to be gained by really understanding structure formation on small scales with cold dark matter and comparing it with observations. Are nearby dwarf galaxies, are there core, is the dark matter cored? Is it a cost? How does this agree with the CDM calculations, simulations? So there could be emerging astrophysical evidence that says it's not cold, or there's more than one component, and that would be huge.
Let's see, is anybody, oh, Paolo. Microphone. Yes, so that's a question for Rob. You said at the end that you don't think none of the above is true. So the basically in proportion. The current experimental efforts are all they're all going with demand to get spent into the weeks. Okay. So if I follow your advice, I shouldn't do that. Because that will be essentially proving
Well,
that
I
the
don't know,
hypothesis is over.
It's like looking at Atlas for physics beyond the standard model.
Yeah. But, so my question is then, do you have any direction?
Do I have what, sir?
Any direction other than that? When an experimental is true, rather than joining this medicine, what would be the other? What is the subset?
Well, I think axions is a very promising, well-developed idea for dark matter. There are experiments looking for it, and the discovery space might be there for axions. Looking for any type of interactions or physics beyond the standard model, whether it's at Atlas or trying to shine light through walls, looking for dark photons, or something like that, could be a path to take forward. I think we do have to run the WIMP idea to ground. There's the coherent neutrino background there. Let's push down direct detection of there, and then do something else. Go maybe to spin-dependent interactions and push that. And so there is work to be done there, another generation beyond the proposed generations. And then I think experimentally let 1,000 flowers bloom. We have to look for something beyond the standard model.
So we've got a reception, and both Rocky and Wayne are going to be at the reception, and you can continue to pick their brains. But before we go to the reception, let's thank them again.